Talk about today is cooperation in static and dynamic networks. And this is joint work with different sort of subsets of people. Winter Mason's a good collaborator of mine. He and I collaborate a lot on how to do experiments on mechanical Turk. Jing Wang was my intern, very, very strong intern. She's a student at NYU Stern. And Duncan Watts is the head of the social networks group at Yahoo Research in New York, which is where I'm based. Okay, so the notion of a social dilemma lies at the heart of what I'm going to talk to you guys about today. Okay? And a social dilemma occurs when the interests of an individual is at odds with the interests of the population that that individual is a part of. Okay? One of the standard canonical examples of a social dilemma is clean air. The best thing for everyone to do is invest in green technology so we all lower our carbon dioxide emissions and we have clean air. However, the best thing for me to do is to not invest in green technology, free ride off of everyone else's investments. I get the benefits of clean air and I don't have to pay for it, right? Now, clearly if everyone behaved selfishly like me, we would not have clean air, and that would actually be the worst outcome for society. So hence the dilemma. The best thing for me, not invest in green technology. The best thing for everyone is to invest in green technology. And that's the notion of a social dilemma. Now, economists have studied this in the laboratory for many years, and they do it using two different types of games. The first is called a public goods game, and the second is prisoner's dilemma. And I'll talk about prisoner's dilemma later in this talk, so I'll talk about the public goods game now. So what is a public goods game, and how does it capture this dilemma? A public goods game is the following. There's n players. Each player has an endowment E, and each player contributes some amount between 0 and E simultaneously with all the rest. And here's the payoff function. The payoff to player P is their endowment minus their contribution. That is how much they decided to keep, okay? Plus the sum of the contributions of everyone else times A. A is a constant factor assumed to be greater than 1. And what this captures is that the public good is worth more than just the sum of the contributions. The whole of the public good is worth more than just the sum of its parts. And divide by n, and what does that capture? That everyone benefits from the public good equally. Okay? And this game is often repeated. So you'll play it, you'll get an endowment one round, play it, you'll get an endowment the next round, play it, get an endowment the final round, third round, play it. And usually what happens is the payoffs sort of accrue, and at the end you get paid that amount in money. Now, how does this game that I just described capture the notion of a social dilemma? What I have up here, I just copied over the payoff function from the previous slide just for convenience. Now, consider what happens if player P increases his contribution by 1 unit. Okay? So what would happen is this term would go down by 1. This will go up, that will go down. It will go down by, this term will go down by 1. Furthermore, the summation would go up by 1. That gets multiplied by a sub n. So the difference would be minus 1 plus a sub n. And that's assumed to be less than 0. Okay? So what does that mean? It means that for every unit that player P contributes, he's actually decreasing his utility. So the best thing for player P to do, therefore, is to contribute nothing. Okay? Now, observe what happens to the sum of everyone's utility if player P increases his contribution by 1 unit. What happens is the following. Again, player P, for player P, this term goes down by 1. And then for everyone, this summation goes up by 1, multiplied by a sub n. But there's n players. So the total amount that the sum of all the utilities goes up is minus 1 plus a. And that's assumed to be greater than 0. So what happens is, for every unit that player P contributes, the social welfare, the sum of everyone's utilities, goes up by more than a unit. So the best thing for everyone to do that maximizes the overall welfare is to contribute fully. Okay? And that's how it captures the notion of a social dilemma. This has been studied by economists for about 30 years. And traditionally, when they study it, they assume everyone plays with each other. And that's going to be our point of departure. But before I go on, are there any questions about what's a social dilemma and how this game captures it? If you don't understand this game and how it captures a dilemma, the rest of this talk is going to be very confusing. Yeah?
As point of clarification, they assume that you play your
So that's what's known as the stranger treatment. And there's there's also what's known as the partner treatment, where you don't get where you just play with the same people over and over, and that's actually what we're going to do. Yeah. Mm-hmm. Any more questions? Yep.
Is the division by then appropriate here, as like in the problem you mentioned for the air pollution problem?
Mm-hmm.
The fact that I'm enjoying cleaner air does not mean that you're living less.
Oh, right. So we're benefiting it equally. It's non-excludable.
So what is divided by n? So is this model correct for that problem?
Yeah. So what it's capturing is that everyone's getting the same benefit, right? So.
In that case, you don't have to divide it by n, right?
Oh, okay. Yeah, I see what you're saying. It's the standard example. I mean, this is the standard game. The point being is that everyone gets whatever the benefit of the public good is, a times the contributions. Everyone gets the same amount from it. And if you don't actually divide by n, you actually get a much different game. Now it's no longer. You might get a game where it's there's no dilemma anymore. Yeah, that's actually what will happen. More questions? Okay, so let me go on. Okay, so where might this happen? Where might you get a social dilemma in a network setting? There's a few places. So consider your favorite social networking site: Facebook, Flickr, Twitter. Typically, if I have post a clever link or a clever status update, typically the people who see it are my friends. It's not a global phenomenon. It's just a local phenomenon. Consider something like polluting the ground or the groundwater. If I have a company and I don't want to pay to dispose of my waste properly, and I just dump it in the ground or the groundwater, typically the effect is local. Another example is property values. If you own a house and everyone in your neighborhood keeps their lawn and nice and their house painted nice, everyone will have better property values. And typically that effect is a local effect. Property values can change drastically from neighborhood to neighborhood. Another example would be upkeep of common areas in apartment buildings and housing projects. Again, if everyone keeps the common areas clean and safe and enjoyable, it benefits everyone, but it's a local effect. It often won't affect the apartment building, a couple miles away. Okay, so now how did we change the public goods game, the standard public goods game, to the network setting? Okay, so now the players are nodes in a network. There's n of them again. Again, each player has an endowment E, and each player P contributes some amount between 0 and E simultaneously with all the other players. So far, it's the same. The payoff to player P is their endowment minus their contribution. That's how much they decided to keep. Plus, and now here's where the difference comes in. It's the sum of the contributions of player P and all of player P's neighbors. Okay? Times A again, right? Now, another difference is instead of dividing by n, we're dividing by D, which is player P's degree. So this captures the fact that player P's neighbors and player P all benefit from the public good equally. And what we're going to do in this work is the graph is going to be regular, so everyone's going to have the same degree. And the reason for that is this is the marginal rate of return. And we wanted to make sure that everyone is experiencing the same marginal rate of return, therefore everyone's experiencing the same gain. Okay, right. Okay, before I go, so now, I'm going to tell you now how we implemented this game in an experimental setting. But before I go on, any questions about the game itself? Anybody? Good, okay, cool. So here's what we did. Typically, behavioral experiments like this with human subjects are typically they're done in a lab at a university with students. I'm at Yahoo. We don't have students and we don't have classrooms. But we have the internet, so that's what we used. Specifically, we used Amazon Mechanical Turk. How many of you are familiar with Mechanical Turk? Okay, great. I gave this talk like a year ago, and it's like nobody. So for the few that didn't raise your hand, Mechanical Turk is an online labor market. It's just a website, mturk.com. Anyone can go to it. And there's two kinds of people on Mechanical Turk. There's requesters who post jobs, and there's workers who pick what jobs they want to do and then do them for pay. And typically, the kind of jobs on Mechanical Turk are things that are easy for humans but hard for computers. Things like image tagging, things like audio transcription, audio translation, website classification, that type of thing. But what we use it for is the labor pool. We use the workers as our paid participants in our subject, and we use it for a payment API. It's a very easy way to pay people. And typically, the tasks on Mechanical Turk are asynchronous. Okay? So what I mean by that is, you put up a task, one person works on it, and he finishes. Then maybe 20 minutes later, someone else works on it, and maybe an hour later, someone comes and they work on it. But I needed everyone to play this game at the same time. And so here's how we achieve that. This took me a while to figure out. What you do is you have a panel of participants who you email ahead of time. Okay? And I'll tell you where this panel came from in a minute. You email them the night before, and you say, hey, tomorrow we're having an experiment at 1 o'clock Eastern time. Please come and play. Okay? And what happens invariably is some people come a little before 1, some people come a little after 1. So as they come in, you put them in a waiting room. Okay? And say you want in 24 players. And what I'm going to talk about today, N is going to be 24. And say 10 people have showed up. Right? So it says in the waiting room, we've got 10 people so far, we're waiting for 14 others. And it counts down. We're waiting for 13 others, 12, 10, 9. And usually after just a few minutes, because you notified enough people, they come in. And then what happens is the experiment starts. But I also want to make another point, and that is the experiment's open to anyone, not just people in the panel. So some people just do come in off Mechanical Turk itself. So then after you get enough, the experiment starts. And then for those of the people who were not in the panel, you just ask them at the end, hey, would you like to join? Would you like to be notified of future experiments? And what happens is most tasks of Mechanical Turk are insanely boring. They find this extremely fun. I have a 90% opt-in rate just because the bar is so low that it's like anybody can cross it. If you're interested in more details about how we did this, Winter Mason and I wrote a how-to guide, and we published it in a psychology methodology journal about how to do behavioral experiments on Mechanical Turk. It's on my webpage. Also, shortly, probably next week, we're going to have a wiki about. We're going to have a wiki that will people can come and contribute to about how they've done their experiments, write code, contribute code, new techniques, new methodologies, and that's going to come next week. Yeah.
How much are they paid? And I assume it's proportional to their wages.
Yeah. I'll give you. I'll get into that later, but just to give you a sense, roughly speaking, we're talking about on the order of like $1, $1.50 per experiment, per subject. I paid a lot because I needed them there in the same time.
Right. I'm actually more interested in the incremental benefit of doing well in the game. If they're doing well in the game, does it mean that they get more money or because it's a prize?
Both. Yeah. Okay. Okay, so here's how the experiment, a little bit more experimental mechanics. Was there a question? Oh, sorry, yeah.
You're about to answer what I was going to ask. How much do you know about the workers, and are you concerned at all that it might be different from, say, the general population in some way that might affect the results?
Great question. How much do I know? I know all kinds of self-reported dynamics. Demographics. So, and I've been doing experiments on Mechanical Turk for about 4 years. So I have a lot of data on Turkers over time. So one thing I did, it's in the handbook, is we looked at people that we've interacted with now and then a year from now. And did they report the same demographics? Were they lying? And the answer is there was 95+% agreement. So if they're lying consistently. And they're remembering it for a year. And if you're going to go through that much trouble, go ahead. That's one thing. Second question. Sorry, you asked me about. Oh, right. Oh, yes. And the second question was more about, is this a sample, a representative sample of the U.S. population? Absolutely not. Is this a representative sample of the population of the internet? Absolutely not. I make no bones about that. What's my alternative? Do it in a lab with a bunch of 20-somethings who are starving for money, often taking econ classes together. So it's a step in the right direction, is what I'll say. And is it the perfect thing? No. But the last thing is, I don't need the population to be representative. I just need that in my treatments, I have the same population. So that any effect of my treatment can be ascribed to the treatment and not a change in the population. So that's actually what I need. So, okay, proceeding. workers had to pass a quiz to make sure they understood it, and also to make sure that, to let them know that everyone understands it. So the guy that they're playing is not an idiot. They all passed the quiz. Most people think people on Mechanical Turk are not very bright. That's completely false. The average worker on Mechanical Turk is far more intelligent than anyone gives them credit for. I thought the pass rate of this quiz was going to be 20%. It was well over 80. Okay, we paid 50 cents for passing the quiz plus a half a cent per point. 45 seconds for the first 2 rounds, 30 seconds for the rest. There was 10 rounds in total. Endowment was 10 points per round. And it just, what you earned per round was kind of stored in your sort of bank. And at the end, we paid them, you know, half a cent per point. The marginal rate of return was 0.4. Where did that come from? The literature. We wanted to compare our work to what was done in the classroom. And so this is a very famous study. We used their marginal rate of return. So the payoff function was 10 minus the payoff to player P is 10 minus P's contribution plus 0.4 times the sum of the contributions of player P and his neighbors. Okay? And most of what I'm going to talk to you about, N was 24. We had 24 players. I will say a little bit about smaller N in a minute. Okay. So this is a little screenshot. It's a little hard to see, so I'm going to zoom in on the right panel, then I'll zoom in on the left panel. Oh, everything in here, this is an iframe. Everything in here is my code. Everything outside this box is Amazon Mechanical Turk. They just give you an iframe. You put whatever you want inside of it. So the right panel says this is round 2 out of 10. You've accrued 14 points so far. Your budget for this round is 10. That's your endowment. Please enter your contribution, and you have 25 seconds left to do so. The left panel is this is you. These are the nodes you're connected to, and each node is annotated with how much they contributed last round. Yeah, Dave? Yeah. More questions? Okay. Right, so I'm going to talk about the results now. So if any questions about the setup? Typical question of the quiz was something like this. We were testing that they understood this was a dilemma. That if you put in one more unit, you got back less. But if you put in one more unit, everyone got back more. So the typical questions were like to test that knowledge. Yeah.
So if somebody doesn't pass the quiz, they don't get the
Yeah, correct.
Was that your safeguard against the sandbox?
For these, yes, that is one safeguard. The other, for these types of hits, where it's just one hit, many assignments, you don't have to worry about spammers. It's just not worth their time. It's not worth their effort to try to spam you. Yeah. More questions? So just, that was an aside. On Mechanical Turk, they're spammers. They typically try to attack hits that are like, I have like 1,000 images, 10,000 images that need tagging. So they can really just plunder you for money. This is just one experiment going on at 1 o'clock. It's not worth their time. Yeah.
So I was trying to think about that quiz. So when this is done in those college kids, do they do that same kind of quiz?
Absolutely. More questions? Okay. Okay, so there's results. So the first thing we did was, like I said, we replicated what was done in the lab. So Fair and Gachter did this well-studied, this famous experiment back in 2000 in Europe. I forget which country. The gray curve is them. Sorry. The x-axis is round. The y-axis is the average contribution level, right, per round. The gray curve is them. The black curve is what we got. And sure, I can give you statistical tests if you want, but those curves are right on top of each other. There's no significant difference in any of the rounds. So that gave us hope that whatever we find on Mechanical Turk will be replicatable in the lab. So this was kind of a calibration test. Is our instrument well calibrated? The answer is yes. Okay, but we wanted to study networks, right? This was done, Fair and Gachter, they did cliques of four players playing with each other. So that's not what we were interested in. We were interested in networks. So these are the networks we used. Okay, the first one is cliques, 4 disjoint cliques of size 6. The second one is paired cliques. And I'll tell you how we got that. So here's how we did that. So this guy used to be connected to this guy, and this guy used to be connected to this guy. And all we did was swap their endpoints. So we just made him connected to him, and him connected to him. So if you have an edge x1, x2, and an edge y1, y2, you just make x1 connected to y2, and x2 connected to y1. Now, we do that twice, you get this. Do it twice more, you get that. Do it a few more times at random, You get this topology, you do it infinite many times at random, you get a random regular graph. Now, why did we use this funny transformation? We did it for 2 reasons. One is it preserves the degree, and two, and the corollary is it keeps the same number of edges the same. Okay? And the third reason I'll show on the next slide. Okay, actually before I do that, let me ask you guys. These are the networks we used. Do you think there was an effect of the network? And if so, which of these topologies had the highest contribution levels? And if I gave it away at lunch or you already heard the talk before, you can't answer. Yeah?
So if I'm playing, and I see that I have these 5 neighbors,
Sure.
do I know that they're neighbors of each other too?
And what I'm reporting on in this talk, no. We actually changed that in later experiments where we showed them not just my neighbors, but if my neighbors are connected, and then we also showed them 2 hops, like my neighbors and their neighbors, right?
So each person sees the same 5 neighbors for all 10 trials, and they don't know anything about how to.
Exactly right. In what I'm showing here today. No communication. So any guesses, any thoughts? Any brave souls? No?
I'm going to say topology has rules.
Okay. The cliques?
Well, and you have 2 competing things, I think. So on the one hand, you have a stronger group structure for the cliques
Huh?
than the random regular. Your contributions are having an effect on by sort of extrapolation or
Okay. So the note, our hypothesis was that the cliques would have the highest one too, and I'll explain why in a minute. So just to put a little bit more meat on it, here's what we thought. There's this notion that people are conditional cooperators, and conditional cooperators behave in the following way: I will contribute more the more my neighbors contribute. Okay, it's a pretty natural way of behaving. It sort of makes some intuitive sense. So this is our hypothesis. Our hypothesis was the following. Say there's a guy, he's contributing a lot. Well, he's going to cause his neighbors to contribute more. But then it said, wait a minute, as these 2 guys are connected, well, he's going to have a positive influence. He's going to have a positive influence here. They're going to have a positive influence on each other. So we thought there's going to be a feedback effect. So we thought the more triangles, the more cooperation. That's what we thought. Yeah?
But wouldn't also the same to the converse apply?
Mhm.
You have a real jerk.
Yeah.
The jerkness spreads.
So the notion of jerkness spreading is going to come up in this talk at several points. So we will call that from here on the Jensen phenomenon. And first observed by David Jensen in February 24th. Okay, so I want to put a little bit more meat on what's your name? Matt's intuition. So I have some characteristics of the graphs here. The left column is the clustering coefficient. Do you guys know what the clustering coefficient is? So it's just the average number of triangles on each node. So it's the numerator is the number of triangles incident on each node. The denominator is the number of triangles possible. And you just average that over all the nodes. So what I'm saying is the cliques has 10 times more triangles on average than the random regular graph, right? A node in the cliques topology has 1.5 times more triangles incident than the small world graph. And he was Matt was saying that the random regular graph has smaller diameter, well, it's kind of infinite in the cliques case, and it does actually go down. But yeah. Okay, so here's what happened. Again, on the x-axis I have round, on the y-axis I have average contribution level. And what happened is, you might think, when you first look at this, the paired cliques, it had the highest contribution levels. And the answer is no, not really. Because any difference in the first round contribution levels has to be by randomness, right? The network could not have affected their first round contribution levels. So in your mind, if you squish these down to start at the same point, these curves are right on top of each other. Or putting it another way, the variation in the first round explains the variation in every round. Okay? So, yeah.
Is there a way of distinguishing between a hypothesis that says that goes down because of neighbors' behavior versus that goes down because my endowment
Your endowment doesn't change. You get the,
Sorry, my current, the current value of my, it's not my endowment, what's the current value of my pot? Don't I have a certain number of points that I have gotten from previous rounds?
correct.
What's that called?
It's your cumulative payoff.
Okay.
Yeah.
But does that change how much I could put in next time?
No, your endowment was fixed.
I see. So I've got this endowment every round. I have the same
10,
endowment.
10 points.
Got it. Thank you.
Yeah. More questions? Okay. So a couple things. What's going on here? So what does this mean? Two things. There's no reinforcement of these triangles. Okay. An increase in cooperation is a strictly local effect. It just, if I contribute more, my neighbors contribute more, and that's it. There was no reinforcement. Okay? Our hypothesis was wrong. In this paper, we go further down this road and consider, we look at the jerkiness phenomena, the Jensen phenomena, further, and we show that, yeah, it does kind of cut equally. That is, the guy who contributes less, the guy who contributes less does, in fact, cause his neighbors to contribute less too. So there was no reinforcement. So I'm actually going to sort of not talk about the rest of the results in that paper. I'm going to fork off and talk about it, some of my latest work, because I'm really excited about it. Yeah?
So is this 23 trials per treatment? Or is
Oh, no, sorry, good question. It's roughly speaking, the 23 trials were, so it's roughly speaking four trials per treatment, roughly. So just to what he was saying is like, we did 4 trials with cliques, 4 trials with small world, et cetera, and you're looking at the average of those, yeah. Yeah.
Was the distribution, I guess you did that before, but was the distribution of the variance across contributions across rounds or across subgroups different?
Yeah, that's a great question. The answer is no. We looked at it. There was no difference in terms of overall, or if you want to zoom in on a group, or even zoom in on an individual. We couldn't find any real significant difference. Yeah.
My memory is in the original, it's the fair experiments, that at the start, something like 8% of the population are cooperating at high rates, 20% at low rates.
Mm-hmm.
So the jerk effect is the dominant effect that's driving this thing down. It's the spreading of the behavior.
So that's a great intuition, and I'm just going to shed a little more light on it right now. Okay. So here's what's known. This is, like I said, this has been studied for about 30 or 40 years. Okay. And what's been known is that there's 3 types of players. There's cooperators. There's people who cooperate a lot. There's defectors, people who defect a lot, and there's conditional cooperators, who I mentioned before. Again, how do they operate? They operate, I will contribute more the more my friends contribute. Okay? So here's what's happening. The conditional cooperators are forced to interact with a heterogeneous mix of other types. Specifically, they're forced to interact with occasionally defectors. Conditional cooperators see someone defecting, they say, hey, he's not contributing a lot, so I'm not going to contribute a lot. And since half the population oftentimes is a conditional cooperator, that causes all the other conditional cooperators to reduce their contribution levels, and hence you get this unraveling. Okay? So here, and this is exactly what I'm going to attack in the rest of this talk. We're going to remove this restriction. We're going to allow all the players, including the conditional cooperators, to choose who they're interacting with. Okay?
Shouldn't the same logic apply to cooperators? There's some cooperators in the group too.
Sure.
And the conditional cooperators, when they run into those people, will cooperate. So is there a differential effect?
2 things. Typically, there's more defectors than cooperators. Secondly, yeah, I don't have the stats to measure this, but my gut feeling is that there's a bigger pull down than pull up.
If you think about it, round 1, the cooperators and conditional cooperators look identical.
Yeah.
Right? And so the only thing that's new information is the defector.
Yeah. That's a good way to say it. Yeah. Yeah.
Is there also a finite horizon effect here? If I can convince people early on to be contributors, and then
So the answer is yes, there is a finite horizon effect. We're going to see more of it. There's always an end game effect in these games. Typically what happens, if you tell people ahead of time this is going to be a 10-round game, typically in round 9, they'll start defecting. Okay? It's known that people can do about 2 or 3 rounds of backward induction, but they don't really do it the whole way back. Okay? For example, in the Nash equilibrium for this game is contribute 0 the whole time. And that's by backward induction the whole way, but people just don't do it. Okay. So now from what I'm going to talk about next is a new round of experiments. How much time do I have? Half an hour? Yeah? About that? Okay. So what I'm going to talk about next is a new round of experiments, again, where we can let people choose who they're going to interact with. Why do we care about that? The point is to let the conditional cooperators, and indeed everyone, avoid the defectors if they want to. Okay? Okay, so the research question is the following. If we allow players to choose who they interact with and their strategies, can cooperation be promoted and sustained? And we're going to show that allowing cooperators and conditional cooperators to avoid defectors results in sustained levels of high cooperation. Okay, so now, just a little bit of motivation. When does this come up? When does this happen, right? Think about the property values case, right? So I keep my lawn nice, I keep my house painted nice, but nobody in my neighborhood does. There's trash all over their yards, whatever. What can I do? One of the things I can do is move, okay? And change who I'm interacting with. Consider the apartment housing example. If no one is keeping the common areas clean and safe, then I can move to a different apartment where maybe my kids can go play in the park. Another example is friendships and work collaborators. So you know, Hannah's one of those stodgy British people. So like I invest more in my relationship with her than she does with me. So I want to not interact with her. But you know, David Jensen is one of those, you know, very nice, you know, East Coast types. So like you know, he reciprocates when I spend more time investing in my relationship with him. He gives it back. So I can change who I'm interacting with that way. Yeah, sorry about it. Stodgy. Okay, now the notion there's been many papers written on methods for enhancing cooperation. Okay, the stack would be this high. Okay, I'm just going to give you a few highlights from that literature. Okay, one thing that works is punishment. One thing that works to enhance cooperation is punishment. How punishment works is in the following way: between rounds of strategy updates, if you know, Hannah, being the stodgy Brit, is not contributing much, I can pay a few points and she'll go down in utility by a few points. And typically that causes her to contribute more. Okay? Another thing that works is rewards. So again, you know, David's one of those, you know, do-good East Coast types. So he contributes a lot. I give up a few points and he will get a few points as a reward. And that typically tends to work. Another thing is communication. If you let people communicate before the game or between rounds, cheap talk works. It just helps people contribute more. These mechanisms are great, okay? And some of them are very realistic, and in certain situations, some of them are very applicable. But like I said, they ignore the fact that people can choose who they're interacting with and their strategies, and that's what we want to do. So a little bit more related to that specific topic, there's a notion of ostracism. It works in the following way. It's actually kind of harsh. So it's like you let people play for a round or a couple rounds, and then you vote on who you want to kick out of the group. So it's like Survivor, okay? And if someone gets more than 50% of the votes, then they go play by themselves, and their payoff is just their endowment, okay? Another way of doing this is exogenous sorting. So what happens is you let people play for a round, then you put, or a few rounds, you put the top 4 contributors in a group by themselves, the next 4 contributors in a group by themselves, and so on and so forth, so you get the bottom 4 contributors. And what happens in both of these cases, they do work in the sense that they do boost the average contribution levels overall a little bit. But really what's going on is that you're just segregating out types. You're just putting people, the high cooperators together, the next high together, and the defectors, they're by themselves defecting. You didn't actually change anyone's behavior. You just sort of segregated them a little bit. And so what we're going to do is actually see that people are going to actually be changing their behavior. And finally, there was some recent work that came out that is similar to what we did, but there's a couple points that are different and very key. What Rand and all did was they let people, they exogenously chose node links at random, and they said, hey, would you like to link to this guy? Would you like to link to this guy who's chosen at random? So it's not me saying, David is contributing a lot, I want to be linked to him. It's chosen at random, and I'm given an offer of a random choice. And the other thing about it is, and what I'm going to talk about, link formation is bilateral. if I want to link to David and he wants to link to me, it's formed. And what they did is unilateral. So what you have in what they did is a lot of, you can have a defector linking to a cooperator and kind of pulling him down a bit. Whereas for us, we have a bilateral. And so, so what we're going to do is we're going to allow each player to endogenously choose their partners, and this is going to result in much stronger effects than what prior work had achieved. Okay, so now I will tell you how we did this in an experimental setting. Okay, so as I said earlier, one way to study a social dilemma is prisoner's dilemma. And here is the payoff matrix we used. And how does this capture the notion of a social dilemma? Observe that the best thing for the two players to do is to both cooperate. And it's easy to see because it's the one cell that has the highest sum of values. Okay? The best thing for the two guys in total is to cooperate. Now, the best thing for any one player to do is to defect. And how do you see that? Say I'm the column player. The row player is choosing to cooperate, let's say. The best thing for me to do as the column player is to defect. I'll go from going from 4 to 7. Consider the case where the row player is defecting, and I'm the column player. Again, the best thing for me to do is defect. I would go from -1 to +1, right? So defecting is a dominant strategy. The best thing for me to do is defect. However, as you can see, it's actually the worst thing for the two of us. It actually minimizes our total payoff. So it captures the dilemma the same way. The best thing for both of us to do is cooperate. The best thing for me to do is defect. Any questions about that? If that's not clear, the rest of this talk is going to be pretty foggy. Questions? No? Good. Okay. Now, okay, so again, N was 24. All players had one strategy, cooperate or defect. We gave them 12 rounds, 12 strategy update rounds, and their points accrued, okay? We paid them at the end, again, ½ a cent per point. Now, the payoffs were the following. So say I'm a cooperator. I would get 4 times the number of cooperators minus 1 times the number of defectors as my payoff. Where does that come from? I'm a cooperator. I get 4 times the number of cooperators minus 1 times the number of defectors as payoff. Say I'm a defector. I get 7 times the number of cooperators plus 1 times the number of defectors. Where does that come from? Right here. If I'm playing a cooperator, I get 7. If I'm playing a defector, I get 1. So that's where it comes from. Okay? And then finally, now, this is one of the key points. How did we let people choose who they're playing with? We call it, the fancy term is endogenous partner selection. The not so fancy term is rewiring. Okay, how do we let people rewire? After every 1, 3, or 6 strategy update rounds, they could update 1, 3, or 5 links. So we did 9 treatments, 3 by 3. Okay? So edge formation was bilateral. It took 2 stages. So if U wants to propose a link to V, U proposes it. Then in the next phase, V can either accept it, in which case the edge is formed, or V can reject it, and it won't be formed. And edge deletion was unilateral. So if either U or V decide they don't want this edge, it will go away. Okay? So I'll tell you that in the next slide. Here's what I want to say. So let's say they were in a treatment where they could rewire 5 links after every 3 rounds, right? What would happen is after round 3, we'd do our strategy updates for the first 3 rounds, right? Then I would get 5 opportunities to propose or delete. So the sum of I get the sum of the number of proposals plus the number of deletes has to be at most 5. That's my budget. Make sense? So there's yeah. And here's what they saw. This is the payoff matrix up here, so we didn't want them to have to remember it. These are the players that are linked to you and their last 5 rounds of behavior. These are the players not linked to you and their last 5 rounds of behavior. Right. So that was the information question. Now, we needed to put them in networks just to get started, right? We need to just have them play with some people just to begin with. So we had 2 initial conditions, the cliques and the random regular. And after that, they could change. Okay, any questions about the setup before I give you the results? No? Good? Okay. So here's what happened. The black curve is the static case. That's the case where they were not allowed to rewire. The baseline case. The blue curve is they were allowed to update one link after every round. Okay? So what do you see? The cooperation levels started higher, they stayed higher, but then there was a precipitous fall. Okay? So what I'm going to talk about in the next few slides is just the effect generally, and then after that I'm going to talk about the reasons for this precipitous fall. Okay? And what I would say is that cooperation levels were promoted, but they were not sustained. Right? And so just to show you that I'm not cherry-picking results, the green curve is three link updates, 3 rewirings after every round. The red curve is 5 rewirings after every round. You get the same effect. Big boost at the beginning, sustained, precipitous fall. Right? So now, let me just talk about the effect sort of more. So what I'm doing here, oh, by the way, I should have said, the x-axis here is round, the y-axis is the average, the fraction of times they chose to cooperate. Okay? Now, instead of averaging, instead of showing it 1 round at a time, in the next slide I'm going to average over rounds. So all 12 rounds will get averaged together. Okay, so on the x-axis here, I have total number of partner updates per player. So consider the case where I'm allowed to update 1 link every 3 rounds. So I'm allowed to update 1 link after round 3, 1 after round 6, and 1 after round 9, right? So that point corresponds to 3 on the x-axis, right? Say I was allowed to update 5 links after every round, right? So after round 1, I could update 5 links. After round 2, 5 links. 3, 5 links. So that's 11 rounds. I could update 5 links. That's 55 on the x-axis. Okay? And the y-axis is the fraction of contribution actions. Again, average overall rounds. This is static, this black dot here. And what you can see is that adding a little bit of rewiring gives you a pretty decent effect. A little bit more, a bigger effect, bigger effect. The effect of rewiring, even a little bit of rewiring gives you a big effect. And then after that, you get diminishing returns. It carries on being increasing. However, the effect is smaller. Okay? On the x-axis here, again, it's total number of partner updates. On the y-axis now is payoff. How much do these guys take home? Okay? Now, again, same thing. Static case down here, a little bit of rewiring results in an increase, but then continued increases in rewiring. Again, there is an increase, although you get a diminishing returns curve. Okay? Now I'm going to walk you through what happened during one run. Okay? So initially, it was the Kleek's topology. And in this case, there was 5 rewirings after every round. Okay? So this is after round 1. They updated 5 links, and the white nodes are choosing to cooperate, and you're going to see some gray nodes in a minute, and those are going to have chosen to defect. So the graph is densifying. There's 1 defector in the top right, but the graph is getting denser and denser. There's 3 defectors, dense graph. Back down to 1 defector, pretty dense. 3 defectors, 2. Okay, now I want you to observe one thing. There's 4 defectors right now, and they're pretty well connected actually. If you sum up their degrees, you get about low 20s. And that's about how many nodes there were in the graph. There's 24 nodes in the graph. So now observe what happens. A few more defectors, a few more defectors, defecting, spreading. The Jensen phenomena has reared its ugly head. So there was a cascade of defectors. Okay? So that's the precipitous fall that you guys saw in that plot, right? So here's, just to put a few numbers on it, x-axis round, y-axis average degree. The average degree just goes up. It doesn't really ever go down, right? They're just adding and adding edges. There's no deletions. What's going on? Why is that? The defectors are not getting punished. They're not getting cut off, right? So I'll put it another way. Of all the edge actions, 52% of them were a cooperator proposing to a cooperator, 24% of them were a defector proposing to a defector, and very little anything else. Cooperators proposing to cooperators, defectors proposing to defectors. Only 10% of the actions were deletes. Okay? Very few deletes. So here's what's going on. I started this by saying, I wanted to let conditional cooperators segregate themselves from defectors. And I failed, right? They're not doing that. In fact, no one's deleting edges. So what's going on? Consider you're a cooperator. You're attached to a defector. What's happening is he's taking 1 point away from you. You could cut that edge and save that point. Or you could propose to another cooperator and get 4 points. 90% of these edges proposals are accepted. Of course, what you're going to do is propose to another cooperator. And you'll just let that defector stay attached to you. If you're a defector, on the other hand, you get positive utility no matter what you do, who you're attached to. So you're not going to delete any edges. So the players were actually not incentivized to delete anything. So, like I said, the conditional cooperators were not cutting the links to the defectors. And that's what caused the jerk effect. That's what caused the defection to spread. So, we attacked this. That's exactly what we attack now. Instead of, in this new round of experiments, instead of there being -1 to the cooperator if it's attached to a defector, we made it -5. Okay? Moreover, defectors used to get 1 for interacting with each other. Now they get -1. This is the new payoff matrix. Okay? So now, if you're a cooperator and you're in this setting, you'd rather delete that edge. Now let's see how this changes things. On the x-axis is round, the y-axis is fraction of contribution actions. Black curve is static. The red curve is 5 rewirings every round, old payoffs. Blue curve, 5 rewirings every round, new payoffs. Okay? What's going on is the contribution levels stay around or above 90%, except for the last 2 rounds. In the last 2 rounds, what's going on is it's just the endgame effect that I referred to earlier. People know the end is coming, they just defect at the end. This is a well-studied phenomenon. It happens in economics all the time. So what I'm getting at is now with these new payoffs, cooperation levels were promoted and actually sustained. And just to show you that I'm not cherry-picking results, black curve is static. Blue curve is 1 rewiring every round with the new payoffs. The red curve is 5 rewirings every round with the new payoffs. And the green curve is something new. 23 rewirings every round with the new payoffs. They could entirely change their neighborhood to anything they wanted to every round. And what you can see is that there's almost no difference between 23 rewirings and 5. Okay? 5 was enough for them to get the job done. Again, the cooperation levels were sustained until the endgame effect sort of kicked in. And now I'm going to show you a run. Oh, okay. Just 2 more plots. X-axis is total number of partner updates. The y-axis is fraction of cooperation. Static, 1 rewiring every round, 5 rewirings every round, 23. So there was no real difference between 5 and 23. A little bit of rewiring had a big jump. After that, diminishing returns. X-axis here is the same. Y-axis is the average payoff, how much they took home. Static, 1 rewiring every round, big jump. 5 rewirings every round, smaller jump. 23 rewirings every round, almost no increase. Small increase. Okay, so now I'll take you through one trial, what actually happened. Okay, again, we're going to start off with the initial graph of cliques, 5 rewirings every round, and this is the new payoffs. Okay, so a bunch of edges got added. After round 1, everyone's cooperating, all the nodes are white. Round 2, after round 2, many edges are added. Again, 100% cooperation. Round 3, this is almost a clique. Round 4, almost a clique. Round 5, 100% cooperation. 6, everyone's cooperating. 7, is it after round 8, everyone's cooperating, 100%. Guess what he did during round 9? He defected, and almost everyone cut their link to him. Okay? Guess what those guys did during round 10? They defected. Everyone cut their link to them. This is after round 11. There's a few more defectors, and they're pretty isolated. And then this is what I'm about to show you now is the final round where it's the endgame effect, and everyone just defects because there's nothing else to do. What about him? Oh yeah, so he defected a few times, and people like, yeah, exactly. He was trying to look good for the end, but it didn't. People were on to him because they had the last 5 round history, right? So and I think it was like 2 ago he was defecting. Yeah. What's that? And you know, you wouldn't either. Okay, so just to put, again, a few more numbers on what you just saw, x-axis round, y-axis average degree. They're adding edges like gangbusters, but towards the end, when people start defecting, they cut them. The degree goes down. The takeaway I want you to have from this slide is this column. 22% of the actions were deletions, whereas last time it was just 10%. So now, there's twice as many deletions as before, and nearly all the proposals are cooperator to cooperator. Let's see here. Okay, so I'm just going to sort of start wrapping up here. So what did we see? What are the insights? What are the takeaway messages? The takeaway messages are a few. From the first round of experiments with the static case, there was no reinforcement of cooperations due to triangles. Increased cooperation levels were a purely local phenomena. I increased my cooperation levels, and that would just increase my friend's cooperation levels, and that's it. It wouldn't go past that. There was no cascade. We saw that endogenous partner selection, or rewiring, can promote and sustain cooperation. Even a little bit of rewiring is enough to get a big effect. The bilateral edge creation was key. It's what gave us way stronger effects than, prior work. But you have to make the deletions worthwhile. If you want to let the conditional cooperators segregate themselves from the defectors, you have to make deletions worthwhile. If not, the defectors will retain their power to have that cascade. That's one of the key insights of this work. And finally, we submit that this is a promising new lever. Endogenous partner selection or rewiring is a promising new lever for promoting cooperation. And so I'll stop there. And this is the handbook that Winter and I wrote. This is the static case, and the dynamic case is under review at the moment. So, thank you. I'm happy to take questions. Yeah?
So, you bring up that it's important to have those huge disincentives to somebody defecting on you when you're cooperating to make people be tied.
It's not huge. It doesn't have to be huge. It just has to be more than the benefit of a cooperator. The CD, the penalty to C, the CD penalty has to be greater than the CC benefit.
And so I guess my question was, do you have any way of, so I think like, I've read a couple people's where you find similar results in lab experiments. You put a giant CD disincentive. Is there, like, what analog do we see to that in real life? So where is that actually the case? Because it would seem like where that's actually the case, that this CD thing is actually bigger than the CC. Where's that happening in real life? So apply this to actual, promoting cooperation.
Right. So that's a great question. Let's see. Let me think about that for a minute. It's a tough question. Like, I mean,
because I guess my thing is it seems to me like a lot of, and I do experimental work in climate, but a lot of things, if we can make it work in the lab, that tells us something really important. But if we can't ever find a real life analog of it,
yeah.
then how do we make it actually applicable in real life?
Yeah. So that's a great question. Like, for example, one thing you could do is like you could measure, the effect of people who are sort of contributing to their sort of property values on their neighbors, measure the externality on their neighbors, right? And you could see is the benefit to everyone cooperating and keeping up their houses, is that higher or lower than the benefit of someone defecting and having a trashy house and bringing the neighborhood down? I don't know the answer to that. Another example might be in these, sort of like clean up the streets campaigns, right? Like if the street is all clean, if everyone in one fell swoop sort of resets back to cooperating, right? Then maybe now defecting actually has a real big penalty because this new damage really sticks out. It doesn't just blend in. I don't have an answer to your question. I'm just telling you places where you could measure it, and then check. More questions? Yeah.
Is the endgame effect well understood?
Yeah, it is actually, and there's papers written specifically about it. Typically, what you can do, and what is done, is you tell players, the end of the game will happen sometime between round 10 and 15. Or, with probability 1/12, the game's going to end after every given round. And what tends to happen is that if you look at, and by the way, there's another thing that people do, which is kind of Cro-Magnon, but it's like, they'll just play the game for 20 rounds, but only report on the first 15, which is a little weird. But what tends to happen with these effects to mitigate the endgame effect is that they help, but they don't remove it. They just, the benefit is like 10%, 20% over what would have happened if you just had the deterministic end. So we just kind of said, why bother? Yeah.
I was actually wondering why people are turned selfish in the end if it doesn't actually help the average or chaos.
Well, defecting is the dominant strategy, right?
Right.
So it is the best thing for them to do, sort of,
They don't trust that other people are going to do it.
it's not, yeah.
Also, the best thing for them to do, irregardless of what, it does not matter what you think the other person will do, it's always better.
So it's a dominant strategy. No matter what you play, the best thing for me to do is defect. So and then when the end of the game comes, they're sort of doing the backward induction, and they only do it 2 or 3 steps, and there it is. More questions? Yeah. Dave?
Have you considered experiments where people have a limited number of links that they can form? It seems in many
Yeah.
situations you can only work with so many people,
Mhm.
you don't have so many friends.
Mhm. So we thought about that. Let me make 2 points. First off, you guys only see like the polished result at the end. You don't see the weeks of agonizing over design decisions. That you could have made this game 100 different ways. One of the ways we thought about making it is say everyone has max degree D, right? No player can have more than degree D. But now, say I want to change a link, right? So I can't propose to you because I'm full. So now I have to delete an edge, right? And then risk that if I propose to you, it gets rejected. And that seemed very complicated and a little less clean. So what we decided was we'll just keep the group relatively small and just try it in the clean way, and then maybe move towards that direction a little bit later. Yeah. We did think about that. I agree that that's a well-motivated question, right? I only have bandwidth to have so many friends, to have meaningful relationships with so many people. So that might be one thing you would try. Yeah? Correct. Yeah, the reason why I did that is because, communication has been studied. Communication over the network setting has not been studied, but it's just kind of hard to build it. You have to build a chat room where some people can see what you're saying, some people can't, and I just like, I had enough hurdles to climb with just getting synchronous experiments done on the internet. I was like, let me not make it harder for myself. Yeah? Good question. Good question. We did allow repeat players, and I know exactly how many times each player played. If you came in the experiment now, you'd be assigned randomly node 12. If you came next time, you'd be node 17, and no one would know it's actually you. So the reputation effect was mitigated. Secondly, we did allow, again, repeat players. We did not see any effects of learning. And in the static case, in the dynamic case, we're still working on that. So yeah.
I came in halfway through, so this is something that you really addressed. I apologize.
It's okay.
Consider a mixed design where you have, say, half, the network is static for half the time in the first half, and then a lot of dynamic. Would we actually first build up a memory of who they swapped with?
That's a great question. But what we had was an initial network, just to stick them in at the beginning, and that the answer to your question is sort of. So what happened is there was an initial graph, right? Now there were some treatments where you could, for example, rewire only every 3 rounds. So the first chance you could rewire is after round 3. So it was actually static for 3 rounds, right? And then dynamic after that. Right. So yes, we did do that. Yes.
And have you played with that window of sort of what proportion of the rounds are
Yes.
at static?
So what happened? We did 1 round of static, 3 rounds of static, and 6 rounds of static. And what you see is that you get the decline. Wait, let me see if I get this right. Sorry. Right. Let me just go back for it. Let me just give me 1 second here. Right. Every 3 rounds, like if this were like /3, like 1 rewiring every 3, 3 every 3, 5 every 3, doesn't look terribly different. This is just shifted a little bit to the left because it's aliased every 6 rounds. This is shifted a little bit to the left. And then for the 1 rewiring every 6 rounds, 3 rewirings every 6 rounds, 5 rewirings every 6 rounds, it kind of looks sort of halfway between static and these. Does that make sense? Yeah. Yeah.
Did you notice with the defectors, since you're reflecting that, any sort of sign of anything about the defectors that was distinct about them, or was it just sort of, it seemed like it was random who a defector was?
To be honest with you, we didn't really, the demographic stuff we didn't really dive into, primarily because it's well studied in literature. Yeah, so we were interested in network effects, so we stuck to those. Yeah. More questions? Okay, then I'll stop there. Thank you all.